Okay, so let's work through a political science example of using confidence intervals on a small data set to test a hypothesis. And what I have in mind comes from a research project that I'm still working on right now. Data that was mostly collected in 2014 um, on the question of party nominations in the US. This is something I think is super interesting. How do parties decide what candidates are going to represent them? So in 2014, along with my colleague John Zoller and four people who at the time were UCLA PhD students, Sean Patterson, Angelo Campo, John Ray, and Knox Brown, um, we studied the winnable open seat nominations for the US House. So I'm giving you some background here so you'll just have some context to appreciate what we're doing. So what we were interested in were the primaries that we felt really mattered. And some facts about primary elections is that most incumbents are not challenged, so you wait till a seat is open. So open just means that the person who's currently occupying it decides not to run. Another thing about the US House is most seats are safe for either one party or the other. And if there's a seat, say that's safe for the Democrats, the Republican primary is really not a particularly interesting thing, and vice versa if it's safe for the Republicans. So we were interested in studying the primaries that mattered in that election cycle. And there were 55 nominations and 53 of them were decided by primary. Some of them were decided by party convention. Um, Fine. The project is really cool. It's more qualitative data than it is quantitative, and the qualitative data is honestly more interesting, I think, than the quantitative data that we're going to use for this example here. But it does have kind of a, I think, easy to appreciate. It does make an easy to appreciate example with the quantitative data. Okay, so for these 53 primaries, one of the things that we have quantitative data on is the number of candidates who ran and their vote share. And so we calculated the effective number of candidates for each primary. If you're a political scientist, that's probably a familiar thing to you. We talked a little bit about the ENC in one of the math camp, one of the really early examples, I think the one about summations, but it's a way of thinking about the number of candidates that gives less weight to people who run and get, 0.03% of the vote. So it's trying to correct for the fact that not all candidates are serious. So we have that data, and there's some conventional wisdom that I was very skeptical of and remain pretty skeptical of, that sort of assumes that most primaries are two candidate races. So the whole logic of having primary elections is this idea that we give voters a chance to weigh in on who their ultimate choices in the final election will be. That works pretty well when there are actually two candidates, and a lot of the work that's done in political science makes that assumption because it's a lot easier to think about. So you guys, if you're reading stuff in the American Core and you hear people talking about the primary median voter and that person being important, that is assuming a two candidate race. So I'm skeptical about this. Okay, so the question that I want to look at here is, are winnable open primaries typically two candidate races? If they're not, the way that we choose them using, first past the post types elections does not work super well. The outcomes can be dramatically affected by candidates that we might think of as spoilers in campaigns. They call them field effects there. All that aside, the thing I'm interested in is whether it makes sense to normally think about primaries as two candidate races. So that's the question that we're going to try to answer with the data that we have with this sample, where each observation, each x sub I, is the effective number of candidates in primary I. Okay, so I have spreadsheet with 53 numbers, one for each of those winnable open primaries. There, effective number of candidates there. That's what I'm going to call my sample. It's not a sample in a literal sense. It was the universe of all the primaries in the category that I was interested in the year that we were studying. But I'm sort of, suspending disbelief about that and hooking my research question into this hypothesis testing framework by kind of thinking as well, these are random draws from the population of possible primary outcomes. This is the part that the more you think about it, the weirder it seems, but bear with me. As I say, it's useful. All right. So I'm thinking about my data as a sample, and I'm thinking about I think my question here as, in this case, a null hypothesis. Okay. So the null hypothesis is the thing that I would like to refute. Okay, the thing I'm suspicious of, the thing I would like to make an argument against. Okay, and my null hypothesis here is that the unknown mean of this distribution from which all the primary outcomes are drawn, I'm going to call that mu ENC, is 2. Okay, so this is the mean of the distribution of those IID primary outcomes. All right, that's my null hypothesis. What I'm going to do now with my data is I'm going to use x sub I to calculate a 95% confidence interval. Okay. I've got these observations, and I've got Stata, which has the t-table built into it, or I've got R, I've got Excel, I've got all of those things. I've got everything I need to take these numbers and come up with my 95% confidence interval. Okay, and then the way I'm going to use that in my argument is if the confidence interval does not, the 95% confidence interval contain 2, okay, then the number 2, the null hypothesis is about here, I'm going to reject that. This is lingo that I think many of you have encountered before. Reject the null hypothesis. This is what I'm going to proceed. If the interval does contain 2, then I'm not going to get too excited. Okay, I'm not going to say, oh, this is strong support for the null hypothesis, because 95% probability is a pretty big interval, and there's lots of other values for mu that would also pass this test. So we would call that, when the interval does contain the value associated with the null hypothesis, that is a null finding, stay calm, no strong conclusion either way. Okay, so this kind of asymmetry of kind of bias built in towards the null hypothesis is kind of part of the idea in science, is that we want to be careful and we don't want to oversell our findings. We really want to have a lot of confidence, word we use, that our data really would be unlikely if the null hypothesis was true. Okay, so what we find with our confidence interval is the range of values for mu under which our data would be 95% likely to occur. So pretty easy for the null hypothesis to pass that test, pretty hard for our alternative hypothesis that no, there's actually more candidates in these primaries and they're actually more chaotic and not working as well as the people in the progressive era who instituted them thought that they were going to. Okay, so kind of a way to think about this is if we end up with a confidence interval that doesn't contain two, that would be the case where the null hypothesis failed an easy test. If the null hypothesis is true, the probability of observing our data would be 5% or less. Okay, so that's kind of the level of that type of error that we would tolerate here. And if it fails that easy test, that's going to justify saying, okay, we're going to reject this null hypothesis. We're going to say that we have a finding here. If the interval does contain two, it just means that the null passed an easy test. Fine. Okay. We don't think that that's necessarily really big news. The asymmetric treatment of studies that reject the null and don't is something that people are concerned about. Sometimes people think that there's too much of a bias toward only reporting results that can be somehow sold as surprising, not enough on confirmatory results. Like many things, I can kind of see the merit of both sides. Yeah. Okay. The other way maybe to think about this hard test, easy test metaphor is when the confidence interval doesn't contain the value that's the hypothesis is about, what we're saying is that the alternative, let me switch colors here. The alternative hypothesis, in this case, that the effective number of candidates in its primaries is actually greater than 2, passed a very hard test. Whereas if the confidence interval does contain the null value, the alternative failed a hard test. Again, maybe not too surprising. Yeah. Okay. I'm going to go on. I'm going to stop here, and I will give you the numbers from my ENC data, but we'll do that in a separate video. I guess the last thing I want to maybe point out before going to the next video is that on this like hard test, easy test, in the pretty recently, last couple years, a paper was published arguing that the 95% confidence interval was too easy a test for a null hypothesis, not a hard enough test for an alternative hypothesis. And the article argued that we should go to 0.995 standard there. A lot of people who I really have great respect for signed that article. Had a huge number of co-authors and was published in Nature. I don't personally quite agree with the argument. I sort of do agree that finding that barely makes the 0.95 cutoff isn't particularly solid. More work should be done, not something that we should necessarily be super sure about. But in general, my thought would be that, like with lots of this stuff about the confidence interval hypothesis testing framework, you don't want to be dogmatic about it, okay? That the 95% confidence interval is a fine rule of thumb, but you actually want to be thinking about other levels as well, so that you don't have to always choose there. Okay, so we'll go on to the next lesson and finish the example of actually calculating this confidence interval.